All right, so last time we talked about ionic compounds, and the nomenclature for those and writing the formulas and names for ionic compounds is generally one of the harder topics in terms of the different types of compounds and the rules that we have. Today we're going to move on to acidic compounds and covalent compounds. By comparison, the rules should be a little bit easier. Acids particularly build off of what we already had done with ionic compounds in general, so they shouldn't be as big of a transition. So if we first dive into acidic compounds, what we need to know in general is what is an acid and how is it different from other types of compounds. Generally, acids are covalent compounds. They're generally small, and they have a hydrogen, at least one, sometimes more than one, that is bound to something that is much more that we call electronegative than the hydrogen. It has a much greater attraction, and it's strong enough that it pulls on the electron of the hydrogen atom a lot more than the hydrogen is able to fight back. And as a result, because of this unequal sharing, when these acids are mixed into water, those hydrogen atoms actually break off from the rest of the compound. They're pulled up off by the water molecules, creating an anion of the original acid compound. So for example, in the two examples I have here on the left, one HC2H3O2, notice that we put that first H in the front there rather than combining it with the other three. And that's there to show that that is the acidic hydrogen in this case. And when that compound is mixed into water, that hydrogen actually is dissociated. It turns into just a lone proton, right? H with one plus. So a hydrogen without an electron is just a proton. And then we have that anion left over by itself. Same thing with the second example, except there we see that it has two different acidic hydrogens, and it can lose both of those in water as it dissociates. So in both of those cases, we see this rough chemical equation. There's no real chemical reaction there going, but the dissociation of those two acids into the hydrogen ions and the cations. Next to each of those, you see that AQ tag. That AQ just tells us that those, what we call chemical species, those things are aqueous. Sometimes it's pronounced aqueous. I go back and forth with how I say it depending on the context. There's no real rhyme or reason. Either of those is appropriate. But that word just means that that substance, that species, is dissolved in water. If we look at what those acids actually look like, again, just to give you an idea of what we're talking about when we say that the hydrogen is bonded to something much more strongly attractive than itself, we have the two compound formulas. The first one here is that first example, HC2H3O2, and then the bottom one is H2SO4. And in both of those cases, we see that the acidic hydrogen is the one that's bound to something that's much more strongly attractive than itself. A lot of times oxygen, sometimes nitrogen, chlorine, or the other halogens. Now, one more note about acids that we'll talk more about when we get into reactions later on is that acids in general have different strengths. All acids have a hydrogen in the formula because they all need to lose that when they dissociate. And so when they dissociate, they increase the amount of hydrogen ions that are dissolved in the water. And that is what defines an acid. It's something that has more hydrogen ions than just neutral distilled water, like pure water. Just like other ionic compounds and things that dissociate into ions, though, some of these acids will break apart easier than others, and this leads to different strengths in the acids. Some dissociate super readily, very completely, others not as much. And in terms of our reactions, when we start doing them, it's going to be important for us to know the 6 strong acids that when they're put into water, they do completely dissociate. Right? So all of the hydrogens will separate from all of the rest of the compound to make only hydrogen ions and the anion that results. Those 6 are listed there. Normally we will memorize them in class, however, obviously you're home. So if you have them on some place that's readily available and keep track of them, that would be fine as well. In terms of naming and formulas, there's 2 types of acids, 2 sets of rules. We have one type of acid that's what we call a binary acid. It's an acid that generally has 2 compounds in it, just like a binary ionic compound. More specifically, though, a binary acid does not have any oxygen present. It's hydrogen and some other element that is not oxygen. So usually that's a halogen, but sometimes it's phosphorus and sulfur or some of the other nonmetals as well. The other type of compound is called an oxyacid, and that's an acid that then has oxygen in it. Noticing that most of those examples that I listed there are similar to the polyatomic ions on the back of your sheet, right? The presence of the oxygen. For naming these compounds, the first set of rules goes for binary acids, the ones that have the hydrogen and one other element that is not oxygen in them. What we do is we have the form of hydro and then blank, and then the word acid goes afterwards. The word acid is going to be on all of these. Hydro represents that hydrogen ion in the front of the compound, and the blank there is going to represent whatever the resulting anion is after the hydrogen breaks off. Now, usually those anions we had been ending with IDE for ionic compounds, but because this is an acid, we're going to have a different ending on that. We're going to make it end into ic instead. So for example here, I could just change my pen really quick. Here we have hydrogen and bromine. Now, when we had ionic compounds, Br1-, we called that bromide. But because this is an acid, we use hydro to represent that initial hydrogen. And then instead of bromide, it ends in bromic. We change the ending from ide to ic for binary compounds. In the second example, we have hydrogen and phosphorus. We know that P3- is called phosphide. But again, because this is an acid, we're going to call this hydrophosphoric acid. And then lastly, hydrogen and sulfide becomes hydrosulfuric acid. For oxyacids, acids that have oxygen in the formula, it's going to be specifically related to what is the resulting polyatomic ion after the hydrogens are separated. And we have two different rules that can apply. If that polyatomic ending ends in ATE, like chlorate, nitrate, sulfate, we're going to change the ending to ic. So instead of nitrate, it would be nitric acid. Sulfate would be sulfuric acid. Phosphate would be phosphoric acid. However, if that polyatomic anion ended in ite, we'd make that ending us. So example, nitrite would become nitrous. Sulfite would become sulfurous acids. In the table here, we see that the rules that we had talked about for different polyatomics, where we can change the number of oxygens and adjust the prefixes or the suffixes to match how many oxygens are in them. All of that still applies here with the acids. Ates becomes ic, and ites become us. So a few quick examples. If we're confident and fluid with the ionic naming, then these should be relatively simple. We just have to make sure we change the endings appropriately. But for all of these, in terms of going from the formula to the name, the first thing I'm going to do is separate the hydrogen from the rest of the compound, because that will let me identify what my anion is that I'm trying to identify. So here we have one hydrogen. Hydrogen has a charge of +1. And we have NO3, and from the back of my polyatomic ion sheet, I know that it has a charge of 1-, or I know that it has to balance the 1 positive of the hydrogen. NO3 1- is called nitrate, and because this has oxygen in it, it's an oxyacid. All I do is change my ate to ic, and then put the word acid. So this would be nitric acid. Here we have 3 H positive ones, and I have PO4, and that would have to have a charge of -3, again from the back of the polyatomic ion sheet, or because it has to match the 3 positive ones. PO4 with a -3 charge is called phosphate. It's a oxyacid polyatomic ion. So phosphate, we change that ate to ic, so this becomes phosphoric acid. Now for our next two examples, I see that there's no oxygen in them, so each of these is going to be a binary acid. So we know that from the start, both of these need to start with the word hydro. And then I'm going to put the anion in there, but I'm going to change that IDE ending to IC. So instead of hydrofluoride, I have hydrofluoric acid. And instead of hydronitride, I have hydronitric acid. Now, noticing that examples number 1 and 4 here both have nitric in them. One is binary, one is oxy in terms of acid types, and notice the difference in their naming. Going from the words to the formulas, again, we're looking for the presence of that word hydro, because if the word hydro is there, it means it's a binary acid, and if it's not there, I need to look for the polyatomic ion. In our first example, there is no word hydro, so I have oxalic, which means that this must be the oxalate polyatomic ion that we have added hydrogens to as the cation. Oxalate is C2O4 with a 2- charge. So to make this thing into an acid, I need to add some hydrogens to it. If it has a -2 charge, I would need to add 2 hydrogens to this to make my final formula of H2C2O4. For hydrosulfuric acid, I know I'm starting with hydro, which means that this is going to be a binary acid, so just hydrogen and one other element. In this case, sulfide, because we have sulfuric. So we have H with a +1 charge. Sulfide, we know, has a -2 charge. So I would need 2 hydrogens to balance that out, which gives me a final formula of H2S. And then lastly, bromic acid. This is not binary. There's no word hydro. So we're referring to the bromate polyatomic ion. Bromate is BrO3 with a 1- charge, which means that I would need to have 1 hydrogen to balance out that and make it electrically neutral to get HBrO3 as my final result. That's the end of acid naming. We'll do a little bit of practice, then we'll look at covalent nomenclature afterwards.